full speed. At the end, a 10 kilowatt, 115 volt direct current generator supplies lighting for the power station and also serves as an alternative to the exciter supplying the field on the main alternator. The traditional marble switchboard had 3 panels. On the left is a Tyrrell voltage regulator for the alternator. The centre panel has all the AC measuring instruments and protective relays, and a wheel to operate the high voltage oil circuit breaker behind the switchboard. The right panel controls the 115 volt DC system. On the pillar at the extreme right is a telephone for communication with the treatment works and the mine. 2 bare telephone wires ran along the edge of the transmission line easement, and a linesman could attach a handset to these at any point to contact the power station or the mine or the treatment works. The transmission line mostly ran in a straight line from near the power station. It crossed several mountain ranges, reaching an altitude of nearly 1,500 metres. It was therefore subject to heavy snow in winter. Close to the treatment works, a short branch led off to the mine entrance. A contract was let for clearing an easement 20 metres wide. Some of the trees were suitable for use as poles, and these had to be topped 10 to 12 metres above the ground. For this hazardous operation, a tall ladder was leant against the tree. This led to the bottom of another ladder, which had been tied directly to the trunk. This upper ladder led to a plank that had been driven into the tree, on which the axeman could stand and then cut through the trunk. The axe is clearly visible here. Finally, a crossarm and 3 insulators had to be attached. Here are 2 photos of the same tree as shown by this oddly shaped branch. The height of the axe here, when transferred to the other tree, shows the huge amount of the tree that is going to come tumbling down when the axeman has finished his job. 59 suitable trees were used as poles this way. For the other 490 poles, holes had to be dug near the middle of the easement. Each pole had to be pulled upright after fitting the crossarm and insulators. The main contractors then supervised the stringing of the 3 conductors. These were 4.5mm solid hard-drawn copper wires attached to 2-part porcelain insulators. A very revealing clause in the specifications stated, quote, "For the last 1/3 of a mile into the receiving station at the works, the line passes through the track of the fumes from the roasting furnaces and those arising from the chlorination plant when the wind blows from the west. It will be necessary to protect these either by very thick insulation or by some preparation which will be durable and reasonably permanent and can be removed. The copper wires originally erected in connection with the works were eaten through at the insulators 2 months after erection, and heavy iron wire was substituted. Here is the treatment works after electrification. The 12 kV lines come into the right end of the substation in the bottom corner. Transformers reduce the voltage to 550 for the various motors and to 115 for lighting. The largest of the motors supplies 300 horsepower for an air compressor. A short branch off the transmission line led to a similar substation near the mine entrance. 3-phase 550 volt power is taken along the 120 metre adit to the machinery chamber at the top of the Cassilis shaft. Here a 75 horsepower wound rotor motor drives a double drum winch. The winch was designed by Mr. Coote and built in the company's own workshops. There was another shaft, the Cerisa shaft, 200 metres away from the substation on the opposite slope of the hill. This had similar equipment with another 75 horsepower motor to drive its winch. A technical paper describing the scheme was published in the Australian Mining and Engineering Review in 1911. It was written by a Mr. Allison, who had worked as a shift engineer in the power station. Technically, the plant was first class, although it had cost far more than anticipated. Reasons given included a rise in the price of copper, extra transport costs due to the high cost of feed, and some unexpected customs duty. Power was switched on in August 1908, less than 18 months from the issue of the tender specification. This was an amazing achievement considering the pioneer nature of the scheme, its remote location and severe weather conditions. 6 months after the completion of the power station, the company's February 1909 report stated, "Owing to an exceedingly dry season, the water in the Victoria River race has not been sufficient to enable us to get the full benefit of the electric plant." And later, a site has been selected for a large storage dam at the head of the Victoria River race, and when the dam is completed, we expect to be independent of any dry summers in the future and will be able to supply surplus power to outsiders. Among all the slabs of text which John Avery wrote on the blank pages of the tender specification, this is the most significant. These are the monthly output figures for the first 16 months of operation of the power station, derived from the kilowatt-hour meter on the middle panel of the switchboard. From these, I have plotted this graph of average power output each month for the first 16 months. The mine and treatment works were out of action for 12 months during the changeover, so an immediate return to full production would not have been expected. However, in December, there is a dramatic reduction in energy used, which lasts until the following May. Then the flow in the Victoria River picked up, and the flat top of this graph suggests that 188 kilowatts was all the power that was needed. By By December, the average power was again down to 70 kilowatts, curtailing the mine activities. Clearly, the Victoria River could not sustain even 188 kilowatts, far less the 400 kilowatt rating of the installed plant, let alone 800 kilowatts if the planned second set was ever installed. I followed the fortunes of the company through the monthly issues of the Mining and Engineering Review. These were available in bound volumes in the University of Melbourne's Engineering Library. These showed a continued failure to tackle the water supply problem. However, in the March 1911 issue, I noticed a Mr. Drummond was quoted as the general manager rather than Mr. Coote. In an effort to learn more about this change, I went to Melbourne's wonderful La Trobe Library. After putting on gloves, I was able to read actual paper issues of the Omeo Standard newspaper of 1910. Sure enough, I found a very detailed account of Mr. Coote being farewelled in April 1910, after about 6 years as general manager. There were glowing accounts of his interactions with the local community, but nothing about why he was leaving. I have tried to compile a list of the company's general managers. The few company reports which I possess do not include any reasons for the frequent changes. However, I did find one in the Australian Mining Standard of the 29th of March 1911. Quote, "The board had previously engaged Mr. A.S. Lilburn to inspect and report on the mine, treatment, etc. Report now received. Mr. Drummond's resignation accepted last Friday. Mr. Lilburn appointed." Unquote. And on the 18th of May, quote, "Mr. A.S. Lilburn reported that a complete lack of metallurgical knowledge was evident on the part of management in both the cyanide and metallurgical processes. He took full charge and management on the 7th of April." Unquote. For the next 4 years, it was Mr. Lilburn who kept asking for the water supply problem to be tackled. One thing that could not be deferred was the need for income. Obviously, a gold mine is totally dependent on selling gold. Here are the production figures for the company. A yield of 1 ounce of gold per tonne of quartz crushed would keep most mines healthy, and some could survive on half this if their extraction costs were low. Extraction of ore ceased during the 1907-08 changeover to electric power. Production then resumed, but the many power shortages and poorer gold recovery meant the company had virtually no income after 1913. Not only was the amount of ore reduced, but so was the yield in ounces per tonne. Finally, in March 1916, The company started the construction of a modest dam across the Victoria River at the start of the water race. Scaffolding 20 feet high was built across the valley to carry double rail tracks. From these, trucks tipped loads of clay on alternate sides. This clay was compacted to some extent by ramming in thin layers. For the outlet, a tunnel was built from heavy logs, and the water discharge was controlled by means of a sliding steel gate. This could be raised or lowered by a worm and screw driven by an electric motor which was controlled from the power station. This was a major improvement. Previously, to change the water flow into the race, the attendant had to go all the way up to the Victoria River. But with this remote control, the flow could be matched to that needed by the turbine. Under the old system, if the load was reduced, the excess water continued to flow and spilled over the side of the race at several places and was wasted. The dam was completed in May 1916. However, by the time the article was published, it had washed away and the mine had closed. This was the last straw, and the government was not prepared to provide any more loans, so the whole company and its leases were offered for sale. Within 1 month, the Cassilis Gold Mining Company was sold, complete with its hydro scheme and leases, to Cameron and Sutherland for £4,735. No buyer considered it worth reopening, even at this price, and everything was sold off at a 2-day auction in February 1917. Despite having left the company in 1909, John Avery maintained an interest in it, and his papers included a copy of the 1917 auction catalogue. 654 items were offered over 2 days, ranging from Lot 648, the water turbine, to Lot 633, a cracked toilet set in the manager's house. This catalogue provides a very complete list of everything the Cassilis Company owned when it closed. I will now examine the validity of 2 very frequently made claims. First, that each year was exceptionally dry for the Victoria River, and second, that harnessing the Kabungra River instead would solve all the problems. The numbered dots on this map are